now used by approximately 100 institutions around the world. For this work, Jeff has earned 8 NASA awards, the JPL Director Research Achievement Award, and the co-authorship of 2 patents. Without further comments by me, I'll turn this over to Jeff. The floor is yours.
Thanks very much. Can you all hear me? Yeah? Okay. I'm actually in an unusual position here of being able to say something about how GPS works, because usually I just come on the stage and give my research presentation and don't have to explain anything about that. So it's kind of a strange position to be in, but I welcome it. And I'm glad to see so many people here who also want to see something about how it works. I'm reminded of when I first started work at JPL in 1985. And for those of you who know Ruth Nealon, who's the director of the Central Bureau of the International GPS Service now, the first couple of days after arriving there at JPL, I was sent out what seemed like a secret mission to the Goldstone Deep Space Tracking Network. It was in the middle of the night. I remember it was about 4 a.m. in the morning. We were going through several military checkpoints, and Ruth pointed to the big VLBI antenna, this huge deep space antenna, and told me that they were being used to measure continental drift. And I didn't know anything about continental drift or plate tectonics at the time. And she explained that we were going to be using a new technique, or developing a new technique to do this, using these much smaller instruments, GPS instruments. And she showed me the instrument, and it was the size of a U-Haul truck, full of wires and electronics and oscilloscopes. And so, I shook my head, and we collected this data and brought it back to JPL. And I said to my boss, John Davidson, okay, so now what do we do? And he said, well, you've got to write some software. So that took about 10 years or so. But we did it piece by piece. There's about maybe 10 to 20 people working on it, and now we've got some pretty good software, I would say. The software Gypsy that JPL distributes. And it's used about 100 institutions worldwide for many different reasons, and I'm going to explain a little bit about how it works. If I can get this to work. Nope, it's frozen. Okay, seems to be working now. Right, okay, good. So GPS is, you'll see use of GPS in almost every section of AGU. And I think it's fair to say it's mainly used in a kind of a black box fashion, but there are certain applications that require quite considerable level of expertise. But many geophysicists use it without thinking too much about it because it works so well. So that's sort of a testament to how well the system works. Starting at sort of the low precision end, you have GIS type applications. For example, just handheld GPS in the field. A geologist might use it for mapping purposes. Often that has a real-time requirement. Maybe it's for navigation. And at the high end, we have geodesy, where we use GPS for geodynamics, tectonics, oceanography, altimetry. You'll see many different types of applications at this fall meeting. And at this high end, there's usually no real-time requirement, but on the other hand, the goal is to get millimeter level positioning in a global reference frame. There are other applications of GPS, measurement of atmospheric refractivity, gives you information on water vapor in the troposphere, stratospheric temperatures, and ionospheric total electron content. And at the bottom I've written here time transfer, although actually GPS really is a timing system by its very nature. So my goal here is to help to prepare non-GPS specialists to jump start you for the more technically detailed talks. So I'm going to really introduce GPS basics and GPS jargon. So for those of you here from the geodesy section, you might just have to bear with me because you probably know most of this stuff. And I'll explain some of the principles behind many GPS applications. I won't really showcase the applications. There's no need for me to do that because other talks will do that. But I do want to say something about the principles so that it'll help you appreciate those presentations. And maybe we can foster some more interdisciplinary research. GPS might be applicable to your own research. And hopefully this presentation will help interdisciplinary communication. And I'd like to give you some awareness of errors from non-familiar sources. And of course, when I talk about errors, it's usually somebody else's signal, and that's the essence of geodesy. So, first of all, I'll explain my own jargon, some basic terms, and then go into what's being measured and what's being modeled, and then summarize GPS positioning measurements, methods, and the typical precision achievable. Often there is questions, fairly basic questions. What about military degradation of the signal? How does that affect me? What data rate should I be using? There are several misconceptions flying around, even in the geodesy section, I have to say. So I want to address some of those misconceptions. This is perhaps one of the most difficult topics. Why are coordinates ambiguous? It sort of gets to the heart of geodesy. I'll just say a few words about that. It's a whole topic in itself. But I do want to raise awareness about the ambiguous nature of coordinates. And I want to show some cool science using GPS, or at least list the cool science. Well, first of all, I can't really assume everybody knows what geodesy is here. It's the science of Earth's time-varying shape and its gravity field. That's a well-accepted definition. It's quite an old science, going back to the ancient Greeks. And it's typically characterized by measurement error being much smaller than the model error. Now, this is true in other fields of geophysics, so it's not unique in that sense. But just to put some numbers on it, you can measure the carrier phase of the GPS signal to within a tenth of a millimeter, no problem. So that's not really the issue. It's not the receiver that's really the issue. It's how you model the observation that's the issue. And so geodesy is a bit like peeling an onion. You model a signal as best you can. You find you've got residuals. It's always systematic, and you just try to peel off the next layer. Try to find the next thing that can reduce those residuals. So today's noise is tomorrow's signal. The Global Positioning System, if you really don't know anything about it, it's a constellation of 24 satellites equipped with atomic clocks. And these satellites transmit timing signals down to the Earth on microwave carrier waves at L-band, and these are the frequencies. It's gigahertz type frequencies. So there are two signals, or two carriers, and a user can position themselves with 4 satellites visible anywhere, anytime. That's sort of one of the design features of GPS. Another term that I'll throw around is the IGS, International GPS Service. It provides GPS data products on the internet to serve geophysical applications. IGS has been around since, the early 90s, and it became official in 94, and we absolutely depend on it. The International Earth Rotation Service, IERS, provides a lot of the models that go into this observation model. A lot of that's conventional now, and people who are writing software abide by those conventions. Also, the IRS provides site coordinates around the world of hundreds of stations around the world that you can use for reference positions. Now, just basically, what's the GPS signal? It basically tells your receiver what the satellite clock time is. So the satellites have atomic clocks. And what the receiver does is it compares the clock times, so it gives you a difference between the receiver clock time and the satellite clock time. And of course, that gives you a time of flight, and that's a range, and with enough ranges, you can get your receiver position. The clock frequency is 10.23 megahertz. It's actually set a little bit lower than this to account for general relativity and special relativity, which, if you didn't account for, would give you quite large errors. That 10.23 megahertz is split out into two signals. It's multiplied by 154 and 120, and it gives wavelengths of 19 centimeters and 24.4 centimeters. So there are two carrier signals coming down that are, remember, fundamentally tied to this atomic clock. So if the clock varies, so does the carrier signal. And then these bits, plus ones and minus ones, are multiplied on top of the carrier, and this basically tells you the time. There's a coarse CA code on the L1 signal. There's a precise P code, which theoretically is only available to the military, but we'll talk about that later, on L1 and L2. And finally, there's a navigation message which tells you the satellite positions and the errors in the satellite clocks. It gives you some other information too. So let's get into this in a little bit more detail. Here's a satellite clock, and here's a receiver clock in green. Basically, the satellite time is transmitted down to Earth. It's picked up in an antenna and amplified. And this is maybe what it looks something like this in the receiver. It's a pseudo-random code. And the receiver itself makes its own replica signal, because this is assuming you know what the code is, of course. And so every receiver is programmed with this information. It knows what to expect. And it generates its own replica timing signal, and then it looks for the difference between them. And that time difference is multiplied by speed of light, and that gives you your range measurement. It's actually called a pseudo-range measurement because of the clock errors. So that's the fundamental measurement in a GPS receiver. I'll get to the carrier phase measurement later, but first of all, what's being modeled? This is where the interdisciplinary nature of GPS comes in, because there are so many things to model. Starting at the satellite, you model the satellite clocks, their behavior. You have to include relativistic effects. The fact that the frequency is set low only accounts for a secular term. It doesn't account for the oscillatory term, due to the eccentricity of the satellite orbits. So you have to account for general and special relativity there. The satellite position, well, you can use a navigation message that's given to you, but it's really not good enough. So to do a real geodesy, you've got to start modeling things better, and I'll talk a little bit about that later. We need to model the Earth's gravity field and its effect on the orbits. Also, non-gravitational forces are very important if you want to get down to millimeter level precision. And it's the pressure of the sun's rays on the satellites which is the biggest problem. So that's solar radiation pressure. Then there's media delay. The signal comes down from the satellite to the ground. Of course, there's a geometrical delay, the vacuum delay. Again, should include general relativity there because it bends the signals a little bit. There's ionospheric delay, which affects the two frequencies differently. And there's tropospheric refraction near to the ground now, and that affects the signal speed, and also it bends the signal, especially at low elevations. And the biggest problem here is the stochastic nature of water vapor. The station position. Well, the stations are rotating with the Earth, so you've got to model Earth rotation down to the millimeter level as well. So we have to include precession, nutation, the UT, which is really the Earth's rotation about its axis. And then there's the motion of the Earth's pole. So there's X and Y polar motion in there. The Earth deforms about something of the order of 30 centimeters or so twice a day through tidal effects. That's a huge effect. It's got to be modeled. So we model tidal effects. There are loading effects from the ocean tides themselves, creating a load and also atmospheric pressure, hydrological loading. Those are all quite big effects. They're all centimeter or more effects. There's diffraction at the antenna, and so the equipment should be calibrated for high precision geodesy. Something you wouldn't worry about with a handheld receiver, but certainly for the millimeter level stuff. And then something that's perhaps not well appreciated is relative antenna transmitter rotation. If you actually turn a GPS antenna, if you rotate it, it actually changes the signal. It advances the signal because the wave is like a corkscrew. It's circularly polarized. You can actually use that to measure rotation. It's been done before. But it is especially important actually if you have a moving antenna, I suppose, on a vehicle. There's also the station clock error, which is the last item there. So we've got to do all of those things well to get millimeter precision in positions. You can see it's quite a big job. So the applications relate to the unknown parts of the model. You're basically assuming that the rest of the model is known, and you're going to focus on your little bit. But if you're really going to worry about the errors, you better appreciate the other bits, because there's a lot of bits to this. Let me just give you some example of the unknowns. Well, positioning is the obvious one, and usually you'll go to an AGU presentation and they're not even talking about positions, they're talking about motions, maybe velocities of stations. But you get that through a position time series. We're not really measuring the velocity, we're measuring the positions and then forming a time series. At the basic level is spatial registration with handheld receivers for GIS type purposes, but it also might be very high precision for positioning, say, the Topex satellite to register the position of the altimeter. There's secular motion applications where you stick out a GPS receiver and leave it for years and see how it moves. For these kind of applications. There's tidal motion. You could use GPS to look at tidal models. There's non-periodic type motions, more stochastic type motions from atmospheric loading, non-tidal ocean loading, and continental hydrology is a hot topic right now with loading. And you might see in several talks on the earthquake cycle using GPS to measure co-seismic displacements, instantaneous type displacements that really take place over a minute or so, where you measure the position before and after, and then you invert for the fault plane parameters of the earthquake. There's post-seismic relaxation, and then of course there's the interseismic phase as well. There's a whole other community which is interested in timing, time registration. Actually, everybody who uses GPS data does this because the GPS data themselves are tagged with what the receiver thinks is its own time, which is in error. That has to be modeled. That's an added complication, quite a headache in the early days of GPS. It's used for satellite laser ranging to register the time of their data. It's used at seismic stations for seismology. It's used for event triggering, to trigger equipment, maybe for photogrammetry, for example. 1 pulse per second signals coming out the GPS receiver to do that. And it's used for clock synchronization around the world, and actually the GPS satellites, since they've got some of the best atomic clocks in the world, they're cesium clocks with the best long-term stability, actually go to the mix, into the pot for defining universal coordinated time. That's the standard reference time. So these two positions, we've got positioning timing, we've got Earth rotation. It turns out GPS is becoming the preferred technique to measure polar motion, which I've got at the end of this list. It's not too good at the other parts of Earth rotation because these parts of Earth rotation reference the Earth to the celestial sphere, if you like, and there really isn't any part of the equations which ties the Earth to some fixed point in the sky. So, but on the other hand, where say the North Pole is right now, you could basically point your finger on the map and say where it is with GPS very accurately. Where is the spin axis in the Earth fixed in the Earth fixed frame? There's precipitable water vapor. GPS is being used to determine how much tropospheric delay there is, and therefore how much water vapor is in the atmosphere. And then there's ionospheric total electron content. Here's an example of figuring out a known or an unknown quantity is the position of a station. If you've got 3 ranges to a point from 3 known points, you can figure out your position. With GPS, it's similar, but you need 4 known points because you've also got to solve for your clock error in your receiver. So there are 4 parameters. And we can get real-time information from the navigation message on the satellite positions, but we can do better than that thanks to the International Association of Geodesy, IAG. We can get orbits and clocks from the IGS. We can get the Earth model from the IERS, and we can also get reference station positions from the ITRF, which is the system of coordinates that the IERS produces. Interpretation of these unknowns requires accurate treatment of the knowns. And there are various methods here of treating the knowns. We could assume models that have over the years become conventional and trusted from IRS, and we could use data from IGS. For example, IGS has got several analysis centers analyzing data from around the world, GPS data from around the world, and they figure out the satellite orbits very accurately, and that saves you the trouble of having to do that yourself. You could do simultaneous estimation of nuisance parameters. These are parameters that are part of the model that you don't really care about, but you've got to deal with them somehow. For example, when you're positioning, you would need to estimate the clock error, but if you're interested in timing, you might need to estimate your position, unless if it's previously well established. Another technique is to form linear combinations of data which eliminate the unknowns. And this is a very common technique used in almost every application. In positioning, we use a dual frequency combination that eliminates the ionospheric delay. So we throw that information away. We also can form differences of data between stations and satellites. Certain combinations eliminate the clock errors. And finally, on the ground, when you're talking about relative position, if you form a baseline, a vector between 2 stations, the error in that is typically much smaller than the error in position in an absolute sense of 1 station, because you're eliminating a lot of errors which are in common between the 2 stations. So we can use differencing methods or linear combination methods. In principle, you can show that these 2 are actually mathematically equivalent. And in some software, some software tends to form linear combinations, and other software would tend to actually explicitly estimate the parameters. And that's a fundamental, it seems like a fundamental difference, say, between Gypsy and Gamut, for those of you familiar with the Gamut software, but really, in principle, it's the same idea. I'll just show you something else here. Satellite positions, in principle, if in an ideal world, they might be fit to Keplerian elements, but this is only true for a very ideal Earth and for a very ideal, and where there are no non-gravitational forces. And in actual fact, there are large perturbing forces on the satellite which cause these accelerations, and they cause these level of errors after one day if you don't treat them properly. The non-sphericity of the Earth causes a 10-kilometer level error if you don't take care of it. The Moon has got a big effect, and so does the Sun. We can take care of those effects very accurately. That's not really the problem. It's not a problem that is so large because we know how to treat it. The problem is when you look at the small effects like Y bias. It's only a 1.4 meter effect only, I say. We're trying to get millimeter positions. And what this is it's really solar radiation pressure. You can sort of have a model of solar radiation pressure on the satellite panels, but if they're slightly misaligned, it will tend to make the satellite will be slightly asymmetric, and it will force it off kind of sideways, and it can produce meter-level errors, and that has to be estimated from the data. The Earth's albedo is also a factor. Just reflected radiation from the Earth pushes the satellites around. Fortunately, the satellites are so high we don't have to worry about drag and magnetic forces. In the navigation message, there's an attempt to take care of all of this stuff by uploading the navigation message every hour. And extra parameters are introduced. I'm not going to explain the parameters, I'm just showing you that they're there. So there's an attempt to do that. But after all of this, the navigation message, which is produced by the Department of Defense, is only good to a few meters. In contrast, the International GPS Service is good to a few centimeters for the orbits. Now, you might be wondering, how do you get millimeter level positioning if you've got this few centimeter error? Well, we're averaging over time. We're also averaging over 24 satellites. And there's also the fact that they're farther away. So you can, the further away the satellite is, in other words, the bigger error you can have out there. It's sort of geometrical effect. Okay, for precision work we measure carrier phase. And here's a sine wave produced by the satellite, and there's a sine wave produced by the receiver. They're at slightly different frequencies because the satellite's moving, so you have the Doppler effect. If you multiply the two together, you get this waveform, which you can show is just simply the sum of a cosine of the difference of phases plus the cosine of the sum of phases. So you've got the sum of two frequencies. If you filter that and get rid of the high frequency component, you just get left with the difference in the cosine of the difference in phases. This is called a baseband filter. It removes the high frequency. And what's commonly called the carrier phase is not the phase of the satellite signal, but it's actually the phase of this beat signal, or the baseband signal. But it's a measure of the satellite phase. It varies with it because that phase there is part of the argument. So, in other words, if that was perfectly stable, then you would be measuring the satellite phase. So the carrier phase measurement is the difference in phases. However, if you look at this equation, it's the cosine of an argument. And when you take the arc cosine, there's an ambiguous number of integers. There's nothing you can do about that, except for the fact that for the very first measurement you make, you don't know what that integer is, but you know it's the same integer if you keep track of the signal. So in other words, that's a constant in time. So at least you can estimate that as a constant parameter, and hopefully, if you have enough measurements, you can estimate what n is exactly at the end of the process. You can actually model a phase as the variation in the clocks by saying the phase is omega times t, where t is the clock time. And then if you multiply by the wavelength divided by 2 pi, you can get an observation equation which looks just like the pseudorange. You've got speed of light times the difference in clocks, but it's ambiguous. But the advantage is that you can measure this to within tenths of a millimeter and not at the meter level. So this really is the key to high precision geodesy. Now there's some complication to this because the GPS signal isn't a sine wave. It's got a code on it too. And the standard method, the handheld receiver type method, uses these bits. It actually makes use of that and doesn't really care about the carrier. But that's not what we're doing in geodesy. We're stripping off the bits and using the carrier. But it's biased by an ambiguous number, and that's a problem. What if the receiver loses phase lock? It means that n changes, and then you get what's called cycle slips. This is what a cycle slip is. You might have heard about that, but not known what it is. It changes the unknown value of n, and it really took quite a few years of development to develop automatic editing techniques that could do this. In the early days of GPS, we would sit down at terminals and try to do it by hand. We'd get it wrong quite frequently, and it would cause precision problems. Ambiguity resolution, you'll hear that phrase thrown around. What it means is estimation of n. So whereas cycle slips determines a change in n when there's a problem, you still have got one n left over at the end of the day after you've done your editing. And ambiguity resolution is determining what that is. This is an entire field of research in itself. It's really gone beyond sort of geophysical geodesy, and it's more in the realm of navigation now, precise navigation, where there are all kinds of methods that are being developed. But this problem for geodesy was basically solved by the late 1980s. But it's essential, and it can be done in real time now, thanks to new techniques that have recently become available. And this just summarizes an analytical view of the observations. We've got 4 observation types, 2 carrier phases, and 2 pseudoranges. And this is what they look like, sort of in a simplified way. We've got the range to the satellite here. Then we have a tropospheric delay, which is some zenith delay divided by a geometrical factor to do, this is just a simple flat Earth layer model. It gets more complex. It's called a mapping function, and it gets more complicated if you include Earth curvature and layered troposphere. But this is just a simplified version to show you basically what's going on. Then you have ionospheric delay, which is different on the 2 frequencies, and it's of opposite sign between the phase and the group delay. The phase delay and the group delay have opposite sign. And then you've got the ambiguity here. Now, one thing you can notice about this set of equations is you've basically got 4 unknowns. If you lump these 2 together, you've got that as an unknown, you've got I as an unknown, n1 and n2, and you have 4 equations. This is one way in which you can actually determine what n1 and n2 are. So there's enough information in the system to determine the ambiguity. That's what ambiguity resolution does. That's why we use pseudorange receivers, even though we don't actually, in the end, care too much about the pseudorange. And that's why we use dual frequency receivers, even though they're very expensive compared to the handheld types. Now, some of you might be ionospheric physicists, and you might care about the ionospheric delay and you don't want to throw it away. Well, so you can use the difference in delays between two pseudoranges to measure the total electron content. And that's because the geometry and clock errors cancel in the previous formula. So the only thing that's different between these two is the ionospheric delay. However, there is a bias in the receiver and in the satellites, electronic type bias, which has to be monitored. And the IGS monitors that and publishes those figures on the internet. In geodesy, we tend to difference away the ionospheric delay, assuming that it's proportional to 1 over f squared. And we form this combination of data, the ionosphere-free combination, and that gets rid of that component. But there is some concern that there may be some residual f1 over f cubed, 1 over f fourth terms, which might come in at the millimeter level. Maybe it's a few millimeters. There still needs to be some research done on that. And finally, as I've already said, we use dual frequency data. It's absolutely essential for robust data editing and ambiguity resolution. So, just to summarize positioning methods and precision, with pseudorange positioning, it tends to be meter level, few meter level, in its various forms. And you can do some fancy tricks like transmit differential corrections, use carrier smoothing. I won't explain really what they are, but it doesn't get you down to the millimeter level, but it's okay for real-time work if you're doing some mapping. So basically, the more money you throw at it, the better you can do in real time there. With dual frequency carrier phase positioning, you can get 1 centimeter in real time if you transmit the data from one receiver to the other, and the other receiver's got software built in to figure out the relative position. That's RTK, real-time kinematic. So you can do that in real time if you're prepared to spend an awful lot of money. It really is a lot. I think it's something like $30,000 for a pair of receivers and radios. If you're willing to wait, you don't have to transmit data over radio. Just process it in the lab. On the global scale, you can get 2 to 3 millimeter positions every day. 7 in height in a global reference frame. If you look at relative positions on a regional scale, it's better than that. It's 1 to 2 millimeters in horizontal and 3 to 5 in the vertical every day. And I just want to say that military degradation really isn't a problem. I've listed the reasons why, but the CA code isn't encrypted, first of all, so you can produce a pseudorange on L1. For some reason, the encryption is identical on the two frequencies, so you can easily cross-correlate the two codes and get a measurement of 1 minus 2, and if you know what pseudorange on 1 is, you can figure out what it is on 2. Why that is, I don't know. So it was very straightforward to get around it with receivers that do cross-correlation. Modern receivers use some other non-classified knowledge about the encryption. The fact that the W code, which is the encryption code, is slower than the P code is used, and so you get, I think there are various terms for it, Z-tracking receivers. They're all sort of proprietary names, but yeah, okay. But that's not a problem. And selective availability moves around the satellite clock. And this isn't a problem because we're differencing out the clock anyway. It's only a problem in real time. And President Clinton ordered that this be turned off in May 2000 for civilian applications. I've only got 2 minutes, so I'm just going to, I'm not going to be able to show everything. But what I want to say is what drives the data rate depends on your application. There's no reason why you can't get a position every second or 10 times a second. Depends on the application. You'll see presentations here measuring seismic strong motion, basically by performing a time series of positions at a high rate. For geodesy, we usually do it every 30 seconds or so, and that's really so that we can edit the data to clean up those cycle slips. It's not really because we need to know the position every 30 seconds. A few misconceptions. The network configuration is crucial for precise positioning. That's not really true. It's true on the global scale. It's absolutely not true on any other scale, because you can position a single receiver using IGS products or using precise point positioning from JPL, and you can do that at the few millimeter level. So you don't have to worry about network design. You don't have to worry about fancy equipment. Atomic clocks really don't change your precision, neither do accurate barometers nor water vapor radiometers. GPS can't do everything. It almost can. It does have some problems with Earth rotation. Another misconception is that you want to try to minimize your daily scatter. You've got to be careful about that, because there are real signals from hydrology that deform the bedrock at the level of 10 millimeters. So if you're somehow washing all of that away, you're doing something wrong, because the signal is really there. You've got to be careful about formal errors from software. They don't really tell you anything about the quality of the solution. Low elevation data. There's a misconception that they shouldn't be used. Well, I'd say they should be used, because it helps to separate station height from zenith tropospheric delay. Data span for tectonics. A lot of papers use N-year data spans. It's actually the worst data span you can pick. Half integer year data spans are optimal for determining station velocities. Differences in coordinates indicate a problem. That's a misconception. Even if the two solutions are perfectly accurate, the coordinates might disagree a lot, and it's got to do with reference systems. That's a paradox, and I really don't have time to explain how that works. So I'm just going to skip to the conclusions now. Let's see. Well, GPS is a timing system, first and foremost. And for the best precision, you need carry phase and dual frequency receivers. There are various methods for dealing with the observation model. You can either estimate away parts of the model that you don't know, difference away them, or you can model them stochastically. And just the key sort of idea to this talk is applications relate to the unknown parts of the model, which requires accurate treatment of the known parts, and various services exist for the known parts, and you should get familiar with them. You don't have to solve the entire problem yourself, but you do have to be aware of the accuracy of these so-called known parts. Thanks.